Problems. First, I want to solve that problem because it's easier, right? And then we will spend the rest of the class most likely massaging this this problem, right? Um, okay, and actually this is part of your homework, right? Here we're going to solve only part A, but also there is part B and C, 3 parts. Okay, so what do we have here? Two infinitely long straight wire. The top one is blue one, current to the right, and this green one, again infinitely long straight, but with the current to the left. The values of currents are the same, 10 amps, right? Then the distance between these wires, L, 4 centimeters. And then we need to find the magnetic field at this point A. It's pretty much part A, and so that's why this point is called A, right? Which is is at the distance D from the center of this top blue wire. And you see the point why I complain about that, somewhat complain about that formula, which author, okay, symbols which the author used in that formula for the magnetic field created by an infinitely long straight wire. You remember mu naught I divided by 2 pi d, because we all know that d is used usually for a particular distance given, like in this case, right? And that's why over there should be r. It's just more natural, more, right? Better. Okay, so what? Physics. Physics is very simple. So this wire creates the magnetic field everywhere. This wire creates magnetic field everywhere. So at any point there will be superposition of two fields. So we just need to take care of that superposition properly. First find the directions and magnitudes of each magnetic fields, and then we need to add them up again using principle of superposition. Of course, we're going to use, so what? No, first of all, I need to write what needs to be found. So we need to find B at point A, right? So of course, for each wire, we will have to use what that magnitude of the magnetic field created by infinitely long straight wire mu naught I divided by 2 pi r. So you see now I use r, not d, because yeah, r is better. And so that's the magnitude and direction, right hand rule number 2. So that's what we need to use twice in this problem. So now let's do it. And you know what, before I start drawing vectors at point A, let me introduce coordinate system, because I want at the end to write it as a vector, because it is a vector. Of course, you can use the words, for example, magnetic field B1 will be into the board, in, right, or out. So yeah, you can use those words, but I want to use vector forms, right? So let me introduce this coordinate system. So z vector, let me point out. So that's z hat. Then what? X this way. So that's x, and y will be up. Right. You remember, you have universal or constitutional freedom to choose any coordinate system you want. Orient in any directions your vector, your axis. So I oriented my system like this, and it's still right-handed coordinate system. Right? So with z-axis out of the board. Right? Okay, and now I want to draw actually vectors. So let's start with this magnetic field created by the blue wire. So first I want to just draw a direction. So in order to find a direction, we need to recall, of course, so that magnetic field lines, they form circles, right? Something like this, right? And directions, right hand rule number 2. So you need to outstretch your thumb in that direction, and then above the wire, magnetic field is going to be out of the board, right? You can imagine me curling my fingers around that wire. So above it's out, and below, of course, it will be in. So let me draw a magnetic field. You see that magnetic field vectors everywhere. Right? So here, blue is going to be, what did I say? Out. So it will be here. I can draw this, 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 and here I can draw this. Out, it's a dot. So this will be B1. Then, for your homework, you're going to have parts B and C. And in part B, you will have to find the net magnetic field between the wires. In part C, you will have to find the net magnetic field below this green wire. So as a result, of course, you will need magnetic field direction below of this. All right, so let me draw. Right. So over here, between the wires, what will be the direction of the blue magnetic field? Again, the same right-hand rule, so but now magnetic field is going to be into the board, into the board, into the board, it's across. So B over here is going to be that way. So it's a B1. And of course, below this green wire, it will still be B1, still have that direction, right? Because, yeah, if this is infinitely long straight wire, direction of the magnetic field below all the way to that infinity will be represented by dots. Direction of the magnetic field will be represented by dots. And at all points below this blue wire, by the crosses. Right, so I can draw these crosses as much as as far as I want, right? But it should be enough. So now let's do the same for the green wire. So green wire, of course, magnetic field lines are going to be again circles. Let me draw a couple. And so what about direction? Outstretch your thumb, curl your fingers. So above, now above green wire, magnetic field is going to be into the board, below, out of the board. Imagine the circle, right? So into the board, it means that over here magnetic field is going to be represented by cross. So that's B2. Cross, remember, it's out. That's what you're going to see if an arrow is going to fly away from you. And this point between the wires, it will be still represented by the cross, B2, right? Yeah. And below, over here, of course, magnetic field will be represented by the dot now, B2, because now magnetic field will be out. This green magnetic field will be out. So you will need, of course, these vectors for your homework. Right. And of course, I can draw these dots, for example. I can continue drawing them as much as I want. Right. So, but for us, we need only these two. Right. And so now we just need to apply principle of superposition. Right. So I will write, so B net equals will be. And you know what? Can you tell me which magnetic field is going to be stronger at this point, B1 or B2? I think it's more or less obvious, right? That B1, blue magnetic field, is going to be stronger because the source of the magnetic field is closer to the point in question. And you see where r, the distance, is in the denominator. So the smaller r, the stronger magnetic field. Right? So B1, of course, is going to be stronger, is going to beat this one. And so the net magnetic field is going to be in the positive z direction. And that's of course, I knew that. And that's why I picked my z-axis out of the board. So that magnetic field will be positive. Who wants to deal with negative factors? Of course, every time you try to make that positive, right? So that's why I picked z-axis out. And you remember you have freedom to choose any coordinate system. So I picked this one to make my net magnetic field positive. So anyway, so now as a result, I will write so B1 minus B2 because I know that magnetic field B1 is going to be stronger. Yeah. Okay, so and now let me write in a vector form. Of course, it will be B1 minus B2 and in a z hat direction. Right. And B1 and B2, of course, can be found by this using this formula. Okay, so now let me write it in this way. So first, mu naught times I. I'm not putting any subscripts next to I because currents are the same. Right? So mu naught I divided by 2 pi and R1. What is R1? Yeah, it's this distance. Let me use black. Yeah. So this will be R1. And of course, now I will use R2 for the second magnetic field. 2 pi R2. Again, what is R2? It's a distance now from the green wire to the point in question. So this will be R2, right? And of course, direction Z hat, or K hat if you prefer. Right. So now, what is R1 in terms of what is given? R1 equals to D. And R2 equals to what? L plus D. So pretty much problem is solved, right? So let me just write those. Mu naught I divided by 2 pi. First, it's a D, right? Minus mu naught I divided by 2 pi D plus L. And in the Z direction, positive Z direction. Of course, mu naught I divided by 2 pi can be factored out. Yeah, you can do it. I will just write down the answer pretty much. Problem is solved. And of course, I already converted centimeters to meters. Right? Distances must be in meters. Because current is given in amps. So, you know what, let me make it look nicer. Just factor out mu naught I divided by 2 pi and Z hat direction. And over here, we're going to have 1 over D minus 1 over D plus L. Okay, so now the final form. And if you plug numbers, you're going to end up with 6.7 times 10 to the power of minus 5 Z direction units of Tesla. And you see, the value of the magnetic field is similar to the value of the magnetic field near the surface of the Earth. On that slide, in one of the slides which I used today, you remember, the magnetic field created by near the surface of the Earth is like 5 times 10 to the power of minus 5. Right. So, yeah, comparable. Okay, you see, this is reasonably simple. You just, and as I told you, students usually don't have any troubles applying that formula.